All right. We seem to be in a Zoom room together.
Yeah. You wanna share to see?
Yeah.
So
let's get that working first.
HDMI. Yeah.
Hold on. What's going?
Does it stabilize?
Maybe
Okay.
segment.
No.
Wait, wait.
Yeah. Does it work this?
So, yes.
Yeah. I'm building your you to make sure I know everything. We need to give it some time till people show up and
Yeah.
see going on Zoom. The problem is that I think the Zoom link was a bit hidden and the advertising. Hope that people know that.
Yeah, no one's on Zoom.
Yeah, but still we are 5 minutes early.
Oh, yeah. All right, let's. Yeah, then I have my video and camera. Or audio and
Audio, we have used that at least.
actually I might no, I'll leave the video. I don't know, might be videos might work better if
That's
it's
it,
not
yeah.
if it's not wasting bandwidth on me.
Exactly. No, it's good.
But, yeah. Okay. We'll look at this later in the video.
Maybe I should put it behind you. Would it be visible if I put it behind you? I don't think so. Right?
Yeah, probably not.
Here, maybe it is.
If I turn off, let me turn off my virtual background.
No, let me put this one. Do not let me know. So I'm gonna put it behind.
Yeah.
Yeah.
Do you have?
No. I hope it doesn't fall over. It's fine. Should supposed to be. Then like.
Yeah. My desk at my proper height anyway.
I think it's your desk in the room is not adjustable, is it? But I think some have adjustable desks here. Third chair here. If you want to sit
Yeah.
around. Is it okay if I record it?
Yeah, I think it's set to that.
Set to that, right?
Yeah.
I did set that.
Yeah.
Perfect. The empty seats here. This room is still there is nobody. I'm not sure about it. But it was and the LinkedIn post, right?
Yeah, that's where I found it. I didn't like register for this event.
Yeah, but there's no,
So I don't know if you register. I assume if you
no,
register.
there's
for
no
it, yeah.
registration required. Okay, I
Nope, someone's there.
okay.
Someone found it.
So hopefully they will show
Yeah,
up.
Milo.
Time.
I sent him the link.
Okay. Okay, let's maybe shall we start?
Yeah.
I mean, hopefully people will show up on Zoom.
Yeah.
Hi everybody. Thanks for attending for another Munich AI talk. So it's a great pleasure to have Professor Johnson with us today. So Professor Johnson did his PhD in Pennsylvania, right? University of
Yeah.
Pennsylvania. And then he joined Carnegie Mellon University as a postdoc. And then he became a professor in the Robotics Institute in basically CMU, right?
Yes.
So he has done a lot of work on hybrid system and control theory, robot locomotion, even design and fabrication of robots. And he's especially known for, again, hybrid dynamical systems and using the theory of hybrid dynamical system to control robotic systems, especially with contact. So without any further ado, it's floor is yours, and we are looking forward to your talk.
All right, thank you. Thanks everyone for coming. I guess what he left out of that is that I'm here at TUM for the next year in Munich as a visiting professor and Hans Fischer Fellow. So if anyone wants to follow up on stuff, I'm around for the next year. So, and all right, so today I want to talk about robots making contact with an uncertain world. And first, just sort of overall in my research group, we want to make robots that can work in the real world. And there's lots of different applications that we're thinking about. One of the biggest ones in the last couple of years has been this environmental monitoring project of sending robots out to dig in the dirt and look for contamination in soils. But we've also done things with manipulation and home assistance and planetary exploration, etc. And in these sort of domains, the questions we ask are, first of all, how can we make robots that can go anywhere in the world and these different applications? And how can we safely and dynamically operate in uncertain environments? And all of these sort of out of the lab, out of the factory kind of locations come with a lot of uncertainty. And so what are the challenges with working in these domains? So on the locomotion side, this was the video playing when you came in. This is like a blooper reel of us testing different legged robots in the park behind campus. And what I want you to think about in each of these clips is that the common theme is unexpected contact with the world. The contact is not kind of what the robot had planned. So here, it doesn't know that it's touching these vines that are catching it on its legs. Other times it bumps into like a branch that it didn't know about or thought it could clear, and instead its foot hits it and it gets stuck. And then other times it thinks it's going to make good contact. It puts its foot down, but it misses, and the foot falls over the edge. And so there's like a missing contact that causes it to fall. And this is not unique to robots. It's a problem for humans too. So this is a YouTube video of a subway staircase in New York City that over time has settled so that one step is slightly taller than all of the other steps. And everyone trips on this one stair because they're moving their legs. They expect your swing leg to make it to the next step. And if it touches that stair before you planned on it, it really wrecks with your balance, right? So this is exactly the same as the robots. And a lot of the stuff we do is locomotion based, but all of these things apply to manipulation as well. So here's another blooper reel from a manipulation paper I was on, where we're trying to pick up small objects. And again, all of these errors, I would say, come down to contact conditions that are different than what we expected. Either the friction is too high or too low, or it goes to squeeze and it misses, or it bumps it early and knocks it out of the way, right? All of these are sort of uncertainty in the contact conditions. So a lot of the projects, maybe all of the projects in my lab, focus around these two key challenges. The first being, we're just gonna pause here. All right, so the two challenges are contact and uncertainty. So contact, and in particular, the discontinuous nature of contact. So when my foot is on the ground, I can get very large contact forces. When my foot is a millimeter above the ground, I get zero contact forces, right? And that kind of discontinuity in our dynamics breaks a lot of the assumptions we have in our state estimation, control, planning, even learning algorithms, assume continuous, if not something smaller, stronger, like smooth or convex in our dynamics. And then uncertainty. These are all domains where we're not going to know the friction on every single rock that we step on, right? We're not going to know how squishy this mud is. And furthermore, I don't think that we can know these things, right? So it's not just that we haven't done enough modeling or we haven't characterized the site well enough, but we're expecting to have variability as we move through. And so instead of trying to engineer away all of that uncertainty, right, like you might do in a factory where you can control the lighting, control the way things approach your robot, the robot, we're just going to embrace that uncertainty and come up with algorithms that don't require a perfect model. All right, and then sooner or later, it's going to be a problem if I can't show any other slides. So let's just restart PowerPoint real quick. 5 slides or 6 slides is all I get, apparently. Thank you, PowerPoint.
You use Keynote. No, you're not mad.
All right, let's see. There's that. Put it back on Zoom. Yep, good. All right. So again, 2 key challenges, contact and uncertainty. So I'm going to go through 3 main projects where these themes come up and how we've addressed them in kind of different applications. And so the first is going to be Kalman filtering, so state estimation for hybrid dynamical systems. And by hybrid dynamical system, I mean systems that have both continuous and discrete state. And so in this case, our continuous will be things like our position and velocity, and the discrete state will be our contact conditions. So how do we do state estimation when we have changing contact conditions? First, just a background, what is Kalman filtering? So this is the, maybe you took a class in this 5 years ago, don't remember. Even if you use it a lot, here we can get some notation and terminology in common. But the idea with Kalman filtering is we're trying to figure out what is our state at the current time. And we're going to represent that as a mean, represented by that dot, and then some probability distribution around it. And in Kalman filtering, that's a Gaussian. There's 2 steps that we're going to do in Kalman filtering. The first is a prediction step where we play our dynamics forward and say, if that's where I was after 10 milliseconds or whatever, here's where my new state is expected to be. And as we propagate that forward in time, we expect the uncertainty to grow, right? Over time, we're less and less certain about where we were because more noise and other things can come in. So then how do we reduce that uncertainty? We take measurements. So let's say we can see some point out in the world, or we can touch the ground, get some sensor measurement that tells us something about our state, right? It says, oh, based on that, I think the most likely position based on that sensor reading is this other spot. And then the magic in Kalman filtering is the optimal way to combine these things to get our new best estimate with a reduced uncertainty from that sensor reading. All right, so there's Kalman filtering in 30 seconds. What happens if we have an impact? So what happens if we have a change in our contact condition? We have this discrete impact, our leg smacks, hits the ground. So I'll explain this for sort of the prediction step, but it's the same idea for either step. And if we don't worry too much about the math down here, but the key thing to know about down here is that when we're predicting our covariance in the continuous phase, we use this A matrix, which is the Jacobian of our dynamics, right? And that's how we propagate that covariance forward. And so that tells us how much our uncertainty will sort of grow and shrink as we move through our dynamics. So for the mean, we know how to simulate our contact event. We can have plastic impact, elastic impact, whatever model of contact we want to have. But then what do we do about the covariance, about the uncertainty around that? And so an initial hypothesis would be to use the Jacobian of our impact law, of our reset map, because that's sort of what we did in the continuous domain. And that turns out not to work. And to understand why, let me introduce this very simple hybrid system. So picture on the left is your leg is in the air, and on the right is your foot is on the ground. All right, but in this one, we've got constant dynamics flowing downwards on the left, constant dynamics flowing upwards on the right. And in the middle is this discrete transition that represents the impact. Only here, nothing is actually changing at the impact. So there's no jump in the state. Nothing moves around there. So nothing is growing or shrinking on the left. Nothing is growing or shrinking on the right. And nothing is jumping in the middle. And yet, over the course of this, our probability distribution has changed. It's gotten sort of stretched out in this way. And so we can see that the Jacobian of the reset map, in this case, there's no jump in the middle, so there's no effect from that reset map, is not capturing the changes that happen when we go through a hybrid system, when we go through one of these transitions. All right, how do we actually figure out what's going on here? And the key ends up being something called a saltation matrix. So the way a saltation matrix works is if you have some variation, meaning like if you have some error or some displacement before an impact, the saltation matrix is going to be a linear mapping to what that variation will be after that transition. All right, so it's mapping these variations through the transition event. And the equation for it starts out with the Jacobian of the reset map. Certainly what your impact law is, what are those dynamics, definitely matter, right? And that's a big part of it. But then there's this whole other part that involves your dynamics before you made impact, your dynamics after impact, the guards, so the transition set, and a lot of state and time derivatives of that. And I'll be honest, the first time I saw this equation, I said, that's way too complicated. There's no way that's important. And I was wrong. This is really what you need to do to capture what's happening when you go through a hybrid transition like that. So I'm not going to go through the derivation here, but if you're interested, we wrote a nice tutorial / survey paper on these saltation matrices, and we have a couple different derivations in there to sort of see where this big ugly equation comes through. But for today, all we need to know is that the saltation matrix thing is what's going to map any displacements before impact into what happens after impact. All right. And if we apply that to covariance now, so here in the bottom here, this is this equation down here. Again, using the saltation matrix, we can map what the covariance was before our transition to what our covariance needs to be after the transition, right? So it's capturing this sort of first order effect of what happens through the transition. So here on the right, if our initial covariance was this red circle, if we just did the Jacobian of the reset map, again, just the derivative of the dynamics along the nominal trajectory, nothing's going to change. So we would have gotten that red circle on the right. Instead, if we use the saltation matrix, we get the yellow estimate, which lines up exactly with the true covariance in black over on the right. All right, so this is the proper way to propagate these dynamics. So now if we go back to our common filtering problem, when we are propagating in our prediction step, our mean follows our continuous dynamics and then our discrete reset. And our covariance takes the Jacobian of that continuous dynamics, but then the saltation matrix for our covariance. All right, and this was sort of for the prediction step. Same happens when you take a measurement. If your measurement says, oh, you've made a transition, you still have to do this sort of propagation. So what does this look like in terms of state estimation? So if we're trying to estimate our state through this very simple system, here at the bottom, I'm showing in red, if we just use the Jacobian of our reset map, so the derivative of our forward dynamics, and then in blue is using the saltation matrix, and in black is using a 20,000 particle filter, which is pretty much what the animation is showing there. And what we can see here is that before impact, these are all the same, right? Because the only thing we've changed is what happens, how are we propagating our estimate through that impact event. And then afterwards, using the saltation matrix does much better than using just that Jacobian of the reset map. And there's still a little bit of error. It's not quite as good as this particle filter here, especially around the transition time. And that comes from the fact that common filtering is a local process. And so we have a single mean, and that mean will impact the transition at exactly one time. So sort of all of our estimate is pre-impact, and then at the next time step, all of our estimate is post-impact. When in reality, sort of some of our beliefs should be before and some after. So that's where that last kind of difference comes. Trying this on a more complicated system. So here's like a springy hopper system. Again, red is using the Jacobian of the reset map. Blue is using the saltation matrix. Here, a lot of the error looks pretty much the same. The only difference is in the y coordinate. So that's the sort of vertical direction, right? And that's because the saltation matrix is a rank 1 update to the Jacobian of the reset map. It's actually only correcting one direction, and that direction is in the normal direction from your contact. So here the ground surface normal is vertical, and so we see most of the improvement is in the vertical direction, right? And that comes from the fact that it's correcting for how long before you make impact in that sort of vertical direction. So the key takeaways here is this saltation matrix thing, which I haven't really explained other than to say it's important, is very important. And it's the way that if you're doing anything with hybrid systems that involves linearization or a derivative, this is the tool that sort of describes how that works through those transitions. So it's key to common filtering as well as many other things. We've extended this to have uncertainty in not just your state, but also in when that transition happens, which is what the animation in the upper right is showing. So the gray is kind of uncertainty in when that transition happens. And we're working now on maintaining belief in sort of multiple modes to handle that transition time a little bit more accurately. we can apply this same idea. So this was, improving our first order approximation at the transition times for state estimation. We can do the dual problem for control and apply this to ILQR. So this is a trajectory optimization approach. I won't go into the details, but at some point you need a saltation matrix, and that's how you get it to work for hybrid systems. So here we're showing quadruped walking, and then we hit it in simulation. If we do the usual convex MPC that a lot of quadrupeds use, it has a fixed sort of contact schedule, and when that gets disrupted, it struggles to kind of catch itself and regain balance. Instead, with this hybrid ILQR, it's able to come up with a new sequence of contacts. Again, because it can reason about how things are changing at that boundary, then it can catch itself and recover from these kinds of disturbances. Here's the same comparison online, only we felt like we couldn't have a very fair way of hitting the robot consistently. So here the disturbance is we cut off all the motors for 150 milliseconds, just let it fall for 150 milliseconds, and then have it catch itself. And that way it can be kind of very consistent. And again, we see that the traditional MPC kind of struggles to find a new contact sequence to recover, while the hybrid ILQR says, okay, let me put my feet down and then continue walking from there. All right, so this whole first section was thinking about cases where we have a good model of our contact. In particular, we have rigid plastic impact. How do we reason about uncertainty and propagate that through these kinds of transitions? Next, I want to talk about a setting where we don't have good models of what the contact looks like. And for this, we're going to think about moving through vegetation. All right, so this is a critical mobility challenge as we can have our robot walk down the sidewalk, but if we want to get off the sidewalk and walk through that pile of plants out there, the contact is going to be much harder to model. It's going to require much more careful control, planning, learning. Sensing becomes a much harder, right? All of these things become a bigger challenge when we're interacting with bushes, grasses, trees, these kinds of things. All right, so let's look at a typical sort of off-road scenario. And I would say, well, there's a lot of papers out there that say, oh, such and such algorithm for off-road robotics. And what they mean is this dirt path down the middle. All right, that's not a road, it's a dirt path, but it's not unlike a road, right? It's definitely harder than being on road. But what about the rest of this scene? So we have a lot of low obstacles that are flexible that we can kind of push out of the way. But then there's other obstacles down there, like that tree branch that's down, that are not flexible, that we can't just push out of the way. We have a wide range of friction and squishiness to the ground. We've got trip hazards everywhere. And then there's some parts where we can just sort of push through the vegetation, and other parts where we can't, like the tree, right? Like, so we're never going to just walk over the tree. We have to walk around the tree, right? Some obstacles you have to go around. It gets worse too, because this is the same spot. It's like sensing issues as well, right? So there's a lot of visual clutter, harsh shadows. We have an obstructed view of the ground, so we mostly can't even see what we're stepping on. We can see the leaves, but not what we're actually touching. And then if we come back a few months later, it looks like this, right? And so now we have time varying environments. Depends on what season you go out there. And especially in the winter, you can see that we have this soft compressible ground cover from the leaves. So if you walk gently, maybe you stay on top of the leaves. If you punch your legs down, you're going to sort of sink in a lot more. All right, so how do we handle these kinds of things? So I think that sort of the key challenge is, we can no longer think about this sort of hybrid system view of, here is when our foot touches the ground, right? And we have a good model of that impact, right? We not only do we not really know when we're touching something, we probably won't even know where we're touching anything. When we have this kind of flexible contact, it's going to be really hard to localize that contact. We also don't have good ways, we don't have good simulation of this, right? So here I'm showing, this is our approximation of a vine that we made out of like 10 rigid links and some universal joints. It's definitely not the dynamics of an actual vine, because that kind of soft simulation is very hard. So that means both that we don't have a model to put in like a model predictive controller, and we don't have a good simulation to run training for an RL policy. And then on the sensing side, we can see some of the obstacles. Hopefully we can see the trees, but we can't see all of the obstacles, again, from the conclusion. And we're going to see a lot of things that are not really obstacles. So in this kind of like forest setting, here's an actual LiDAR scan. All of those pink dots are a LiDAR return from some little twig that was sticking up, or a blade of grass or something. And if you pass that into your planner, it says, well, there's no path through this space where you don't contact something, which is true. You have to bump into stuff. And so we have these sort of major sensing challenges. So what I'm going to sort of advocate for here is that let's think about how are we going to handle vegetation at kind of multiple different levels. And here I've got our model-based hierarchical control scheme. But I think the ideas apply to whatever kind of control scheme you have. Maybe some of these are learned policies instead of MPC. But the idea is that at the highest level, at your sort of task planning level, you need to adjust your path to go around the big obstacles, right? We got to go around the trees and the big rocks and that kind of stuff. So we need some high-level planning. We want to adjust our gait to maintain our balance and wiggle out of obstacles. At the kind of foot swing level, we need to come up with ways of disentangling our leg, right? So as the foot is moving forward. And then you can even think at the like low level joint, usually this is a PID loop, that the joint sort of stiffness level, how do we achieve our plan? Sometimes we just need to push harder, right? If you're pushing up against something. Other times, if it's a rock, that's not going to work. So we need to have a reaction we need to think about our response at each of these different levels. So I'll start at the kind of inverse dynamics at this green level here. And our approach to handling vines and obstacles, there's two main parts. The first is going to be a link momentum observer. So how do we know that we're caught on a vine or other obstacle? And the idea with a link momentum observer is that we have a model of our leg. We don't have a good model of the vine, but if we compare what our leg is actually doing to our predicted momentum based on our model, if that deviates by too much, we must be touching something, right? And this won't necessarily tell us what we're touching, and we may not be able to predict what the force will be, next time, but we can know if we're hooked on something that's preventing us from following our desired trajectory. And then if we know we're touching something, let's come up with a reactive controller that can get us unstuck from anything. So here we're simulating a whole grid of vines. Pretend each one of those things is a vine, and we're modeling it here as just like a spring damper kind of thing. But we're going to come up with a leg trajectory where no matter where we're touching the vine, we're going to sort of slide all of those contacts to the bottom of the foot. We're going to advance it with the leg folded up so that the vines touch the back of our leg, and then extend our leg down. Right? And this way, no matter where we're touching, no matter what the force properties of that vine are, we can continue making progress. All right, so what does this look like if we put this together? So it's going to walk. It's using this link momentum observer. So when the leg gets hooked, it says, I'm touching something. Let me do this recirculation, get my leg unhooked, and continue making progress forward. All right, and so this way we have huge uncertainty we don't have any real model of the vine. We don't know where we're touching it, but we've come up with a strategy where we don't need to know any of those things, right? And that's what gives this the robustness. So here it is on the robot working on a variety of obstacles. So we've got low stiffness as a bungee cord. This is kind of like our vines. We've got a stiff rope in the upper right that's not springy. We've got a rigid beam. So this is just a metal plate. And then the bottom right is all of the above mixed together in some kind of robot torture device where it has to get through all of the obstacles together. But again, because we're not trying to estimate the stiffness of the vine, We're not trying to say, oh, here's where we're touching this one. There can be two things touching. There can be hard and soft mixed together. It doesn't really matter. And then my favorite, actually, here, we took a soccer net and laid it out horizontally. So it's just a field of things to get tangled up on. And certainly, it kind of trips a little bit, as you would expect, but it's able to then get its legs disentangled and continue making progress forward. All right, so this was, again, how we sort of disentangle at the sort of leg retraction level. If we go up a level in our kind of control hierarchy, now, all right, so we can now advance our leg. We can take another step, but we may not know what we're walking on. So here on the left is the robot's model of the world. Here on the right is what it's actually walking on in simulation. So this is like the case where you have grass or other vegetation. You can have a camera, you can have a LiDAR, but that's mostly going to see the top of the grass and not what your legs are actually walking on. So for this, we can use our proprioceptive sensors, feel where the ground actually is, and build up a map of the terrain as we walk around. Right? And then now we can then plan on that map for the next step. Right? So maybe I kind of, maybe I'm not expecting there to be a mound of dirt right there, but as soon as I touch it, now I know that's there, and I can plan accordingly as I continue moving forward. Right? So we reduce that dependence on exteroceptive sensing that's going to have occlusions. And then we can go to even higher. Again, there's lots of ways to do this. The short story is go around the trees, right? We're not going to try and do this leg disentangling thing to walk through the tree, right? We don't even want to do the proprioceptive thing. I mean, we could walk into the tree and then tell that we stopped making progress. But for the big things, we want to use exteroceptive sensing, see that there's a tree, plan around it. We've written some papers on path planning, but any kind of high-level planner, we still want that at the kind of highest level. All right, so what have we learned about sort of walking through vegetation? I think that we need an approach that, I think modeling the vegetation is kind of the wrong direction to go. There's too much variability. We're never going to know these parameters. Instead, let's come up with approaches that don't require a perfect model and can be robust to huge amounts of uncertainty in the state and in the model. And then we need to think about how to handle this at kind of different levels of our control abstraction. And then I should mention also all of the quadruped control stuff that I've presented here that we've done in the lab. This is all part of our Quad SDK open source control stack. So if you want, you can download the code and run all of these examples afterwards, including the vegetation disentanglement and all of that. This is sort of, I would say this is sort of a pretty standard control stack that then most of my students take this and then, oh, let me try and beat this with a learned controller, or let me replace the state estimation, right? So we sort of build out from here. All right, and then the third thing I wanted to talk about today was learning how to drive over different kinds of challenging terrain. And first, just thinking about the platform that we're using here, legs are very good at getting over rough terrain, and this is kind of what the legged community has been selling for many years of, oh, if you need to get over rough terrain, you got to have legs. This was from my PhD. This was before we had all the quadrupeds. But now the whole quadruped market, oh, if you want to get over rough terrain, you need legs. But it turns out that wheels are pretty good, especially if you have still a mechanically capable wheeled platform. And wheels are kind of put up as our best invention ever as a species, right? The cartoon image of invention is the caveman making the wheel, right? Wheels are pretty good. And here we've got this wheeled platform. It has a good suspension. It's got a lot of passive mechanisms in there. It can handle a lot of that terrain. The only caveat is you need to have a pretty good driver, right? When I drive it, it flips over, right? But when my grad students drive this robot, they can get over these huge rocks, large obstacles that maybe traditionally people say, oh, you need legs to get over a big rock like that. So how do we make this kind of off-road driving with a more capable wheeled robot autonomous, right? so that you don't need the well-trained grad student. So a lot of these challenges are the same as before, but again, we're not going to have a good model of the environment, right? Maybe we'll have some geometry for where the rocks are, but I'm not going to guess what the squishiness of those leaves are. And so we really need to think about sort of stochastic dynamics. We need to think about how that uncertainty is growing. Collecting data is very expensive. So robot time takes actual time. And if you collect thousands of hours of data from your robot, you have a different robot at the end than you do at the beginning because it's worn through all of its bearings, right? And picked up some dirt along the way. And so it's hard to directly learn in simulation because we don't have good models. But then it's also hard to learn in the real world because it's too expensive. And then we want to think about many different types of terrain. So there's kind of infinite variability there. And we also need to do sort of long horizon predictions, right? So we need to approach the rock from the right angle. We need to make sure that we don't get stuck high centered on something. So we need to be planning ahead and not just reacting. So I'm going to go through a lot of the sort of components that go into our solution to sort of learning how to drive over different terrain. All right, so I think the first ingredient you need is that we should be making closed loop probabilistic predictions. All right, so the open loop dynamics here are very unstable, but we're never actually going to run an open loop controller. We're going to close the loop. We're going to have sensor feedback. And so when we're planning, we need to be planning according to that closed loop prediction. And secondly, we need to be making probabilistic predictions, right? We're not going to know exactly what the friction is. So let's account for that uncertainty and think about how that's going to grow and shrink over time. Then once we have these probabilistic predictions, we need to constrain what I'll call the divergence of the trajectory. So here, if we want to go up this slope, let me actually pause. I like that last here. All right, so here, if we just do a single trajectory plan, we'll come up with this red trajectory. And our nominal model thinks we can make it up this hill. But actually, the friction's slightly different, and the robot can't quite make it. All right, so here we see the actual robot in green is kind of, oh, you can't see my cursor. So here's the nominal model in red, thinks we can make it up the hill. When we actually run this on the robot, in this simulation, it drifts off to the side because it doesn't have enough traction. But if we look at, again, if we have a probabilistic dynamics model, we can watch how this collection of predictions diverges. And in general, we want to avoid places where it really blows up, right? Because, yeah, maybe in some worlds, we can make it up the hill that way, but the chances are pretty low, right? So we want to look at not just the magnitude of that uncertainty, but in particular, how much it's growing or shrinking in any one time step. And then we want to ideally find time steps where that uncertainty is reduced, but at a minimum, let's cut out the time steps where it blows up like this. All right, so we call this divergence constraint optimization. Here it is sort of on the robot. You can see these red particles. Some versions of the dynamics think we can make it over that obstacle, but not all of them. If we just sort of penalize that instead of constraining, then you get kind of really conservative behaviors where it doesn't want to allow for any amount of uncertainty. And that's why instead we want to constrain the growth on the uncertainty and come up with plans that are maybe a little bit longer. We have to go around, take the ramp, but don't have too much uncertainty. All right. Next piece is that we still want to use lots of simulation. All right, simulation is a great tool. It's cheap. Now we know that it's wrong, right? We don't have a good model, but it's close. It roughly looks like driving, right? So how do we use a lot of simulation that's wrong, but readily available? And so what we're going to do is we're going to randomize the domain, right? But unlike most sim to real methods, use this domain randomization and throw all of that data into one big bucket. Here we want to keep these different domains separate. So on the right, I'm sort of representing by the colors. These are different versions of the dynamics. you can kind of see some of the robot bodies are longer or shorter or wider, but we're randomizing the mass and the friction and all sorts of different parameters. But we're keeping all of these separate. And then in addition to learning our dynamics, we're also learning what we call a sys-ID transformer. We're trying to do system identification in parallel to the dynamics prediction, right? So that if we can learn kind of where in this sort of model space we are, then online we can use a little bit of data with this system identification to come out to figure out what our current model is. So we use lots of simulation that's wrong but cheap, and then we combine that with a little bit of real world data. And by little bit, I mean on the order of 10 seconds, 5 or 10 seconds of robot data, depending on what you're doing. Then online, we're going to take our actual observations, pass it through that same sys-ID transformer, and learn kind of what our current context is. And so this allows us to adapt to different terrain, but also different wheel friction and throttle gain and steering and all of these other things. Finally, the last piece here is to then wrap this in a risk-aware controller. We're using MPPI for safe control prediction. So we have this probabilistic dynamics model. So we need a controller that can then reason about that and not take any actions that are too risky based on our dynamics. So with this whole system together, let's see, on the top is if we is kind of what we're training, and we see that the lap time after, these are in seconds. So, in a few tens of seconds, we've adapted very quickly and reached kind of our optimal performance. And this is the number of violations per run. We're getting like 0.00, very small, 99.9% accuracy or success rate, very low failure rate. If we just tried to train with data from the actual dynamics, not using this simulation, that's what we're showing in red. And the key point is the scale bars are not even on the same scale, right? That we need thousands of examples before we can start to have a good model of the dynamics. So what does this look like? If we train a policy with just our one best simulation, so we'll do whatever sys-ID we need to do once, get a good model of the robot, and then try and run it on different terrains, try and run it with different, we've swapped out the wheels for different friction, different masses. We see that it falls off the course or it rolls over and struggles on these different terrain. Then using this sys-ID transformer to adapt the model online using a little bit of data, we're able to handle all of these different conditions. So both, again, this is both the terrain, but also the friction, the mass. We're changing a lot of things between the charts. All right, so we had like a lot of pieces here. So to put this all together, right, we need to have adaptive dynamics models where we're simulating different variations, but then training both the dynamics prediction, but also how to tell where we are among these models. And then we're doing closed loop divergence constraint planning to come up with robust trajectories based on that model. All right. So a really simple example here to show how this is working. So we've got two versions of the system. On the left, we have low friction wheels, and on the right, we have high friction wheels. And when we first start up the system, and there's no kind of experience yet, we don't know anything about this system, the two systems act the same, right? There's no difference in the data going into them. So they come up with this less direct route to the goal. It's not confident it can make it over the hill, so it'll go around the hill. And it's actually kind of interesting. It can reason about, even if it's not sure about its dynamics, it can probably drive down the stairs, but it's not going to try and drive up the stairs. All right, so this is kind of the initial robustness is coming, so initially it comes up with policies that work kind of whatever the dynamics. Now let's give it a little bit of data from the system. So we're going to give it one observation. So this is the only data we're feeding in from the actual system. And that's trying to drive up the stairs. And in the high traction system, we can drive up the stairs no problem. And in the low traction system, it gets stuck. It can't go up. All right. So this is when I say just a little bit of real world data. This is the only data from the specific system that's going in. And then after we take this data, then the sort of adapted control policy, the next time we ask for it to go to that green circle, for the low traction system, it's still taking the long way around because it can't make it over the hill. But the high traction system has learned that it can go up this steep slope and over and have a much more direct path. And this is even though we didn't give it any examples of it driving up that slope. We sort of only showed it the stair climbing. But it sort of learned that, all right, if, you know, generally if you can drive upstairs, you can also drive up ramps and other things. All right. So that's sort of how this, again, we sort of described this learned control system as initially robust. So the initial policy works for all of these cases. But then with a little bit of real world data, it's able to be adaptive to the specifics of the system. All right, so what have we learned from this sort of learning how to drive section? So we want to consider both epistemic and allotoric uncertainties. We want to consider the uncertainty inherent to the world, but also the uncertainty that comes from the fact that we just don't have enough data yet. So we have to sort of initially collect some data, and as we go, maybe we'll become more confident. We want to combine lots of simulation because it's cheap, but it's wrong, and then find a way to combine that with a little bit of real world data. You know, if we just took that real world data and threw it in with thousands of hours of simulation data, it's not going to really affect anything, right? It'll get just drowned out by the simulation. So we need to come up with clever ways to combine lots of simulation data with a little bit of real world data. And then finally, think about the sort of divergence and our uncertainty to make sure we don't take overly risky actions as we're going. All right, final thoughts. I covered way too many things in this talk. But I think the common theme from all of these was that we need to carefully consider our contact conditions. And that's true in mechanical design, in control, and sensing, and learning. We need to develop strategies that work no matter what the uncertainty is. And so not just come up with strategies that try and reduce that uncertainty, but come up with strategies that are robust to that uncertainty. And then we should be reacting and adapting at kind of multiple levels. Right. So we need to be thinking about sort of short-term adaptations, long-term adaptations. There's multiple timescales that work here that we should be considering. There's lots of other work going on in my lab that I didn't have time to talk about. I did bring, although I didn't talk about him in the upper left here, we've been making some small biped robots. Or hold this for in case anyone's on Zoom. So this is 2.5 centimeter leg length. We call this one Zippy. And he's actually really fast, so he can run at 10 leg lengths per second, which makes him the fastest biped out there. We've also done some stuff on, again, design and state estimation and control on the manipulation side with these direct drive grippers that are very transparent. They can kind of smack into the table and pick things up. We're doing paleo-inspired robotics, so I have a paleontologist in my lab, which I think it's like if robots weren't cool enough, we're doing dinosaurs now too, all right? So what can we learn from the fossil record that can tell us something interesting about robotics? And then I just had a student yesterday defend his thesis on multi-agent control and coordination. We're using a lot of the same ideas about MPC and uncertainty and that kind of stuff. Before I end, I just want to say a few words about supporting diversity in robotics. So hopefully it's not a surprise to anyone here that the diversity of the robotics community looks nothing like the diversity of the rest of either the country or the world. And what's more concerning is that these diversity lines are not really changing over time very fast. So there was one study looking at percentage of women in robotics, and it showed while that is improving over time, we aren't going to reach gender parity until 2050 something, right? It's moving like very slowly. And so it's clear to me that we need to take some concerted actions to think about how we're running the system and what we can do to improve this. So I've got some suggestions here for what you can do either as an individual, as a research lab, as a university, or as a robotics community. And the first is to join a networking or advocacy organization. So I've done a lot of work with Black in robotics, but there's also women in robotics, queer in robotics. You can think broader, Black in computing, Black in engineering, sort of broader communities. I invite you to read, cite, invite, mentor, and collaborate with a diverse set of researchers. So if you came out of this talk saying, man, I got to read some more papers, maybe don't go to my website. You can go to the Black in Robotics reading list and find interesting research from maybe someone you weren't aware of that's in your area. And finally, I invite you to just spend a little time learning more. So we have this article supporting Black scholars in robotics, and there are these great action item lists from Black in engineering, Black in computing that have a lot more ideas as well. And with that, I'll wrap it up and take any questions.
Great, thank you very much. Any questions?
Yeah.
Yes, Judan, you can start.
Regarding your comment, since you repeat this, it's wrong to have infinite number of simulations, you give us some insight, because it looks like the fluid now is doing this a lot.
Sorry,
For the drug,
the drug. Yeah, so we do want to do lots of simulation, right? What I'm saying when I say that it's wrong, I mean the prediction, what the simulation outputs is not going to be exactly what the robot does in any given trial, right? And so especially if we're going on, grass or some other terrain that we don't have a model of, we can play with different friction parameters in simulation. We can get a variety of driving behaviors in simulation, but it's not that any one of those would correspond with this robot driving on this terrain, with this payload, after it's rained, right? All of these sort of infinite variability. So, and that's what I say, when I say that the simulation is wrong, that's what I mean, is that we don't think that it's going to ever predict exactly what's going to happen in this situation, right? It's generally looks like driving, right? So that's why we want to try and capture that sort of general behavior. But we don't want to say, we don't want to just do a model predictive controller with that as the model, or just learn a controller based on that simulation model, because we don't think that that's going to be accurate, especially when we're sort of pushing the boundary on the sort of environment. Maybe we could have a good enough model of the robot itself, although even there, you throw a new payload on it, or you've run a lot of trials, so the bearings are starting to wear out, right? Or the tires not inflated all the way, right? So there's still some variability in the robot. We're probably better at capturing that variability, but I don't think we're ever going to capture, all of the different terrain we can drive over. And so it's kind of freeing, actually, because now we don't have to have a perfect model. Like if I put a new payload on there, I don't need to figure out where the new center of mass for the system is, right? And what the new inertia is of the system, right? Because they're not trying to have an exact model. Instead, we're coming up with approaches that don't need an exact model. So it's actually very freeing in some ways, that we don't have to constantly be trying to improve our simulation.
Additional question regarding driving. So compared to, for example, classical method where we have a good model, a physical structure or class of models, then we can do cube MPC. In this case, you are sampling different vectors. So is there a coverage problem? For example, if we think about the disturbance inclusion, is this for this sample, how much percent can our all possibility disturbance?
Yeah, so I think, if you think about all right, let's think about all the different ways that our variability could be off, right? We've got friction on the tires. We've got the mass of the system, the center of mass, maybe with the wheelbase, maybe our geometry is a little bit wrong, right? We can come up with infinite dimensions of ways that our model is wrong. But at the end of the day, we're driving, right? And so if you think about what's the space of driving behaviors? Well, sometimes when I press the throttle, I go a little faster, and sometimes I go a little slower. And with steering, same, right? Sometimes it's a little sharper, sometimes, right? And then maybe there's a little bit of when do I slip versus stick. But the space of kind of driving behaviors is actually, I think, much lower dimensional. So I think, I forget how many dimensions we had. We have sort of a latent space representation of that. It's something like 3 dimensions or 5 dimensions. It's something really low, much smaller than the number of dimensions of variability that we're capturing. Because we're not trying to do cis-ID, so we're not trying to figure out what's our friction coefficient and what's our mass and what's the stiffness of the spring and all of these other things. But the sort of behavior level is a much lower dimensional system. And then in terms of sampling, we're now sampling in a much lower dimensional system, so we can get better coverage rather than sampling in this high dimensional system.
Another question, very short. So for those trajectories, there is no like rule. There are different.
For those, like when we show like the different rollouts, like in, oh, not that one. You mean like in, I don't know, like in, yeah, this, no, that's the no uncertainty one. This one, yeah. Yeah, so these are independent samples, but it's, each of them is a closed loop prediction. So if in that sample you get bumped a little bit more to the left, then you assume that you adjust, your steering accordingly in like a closed loop control. But they're independent samples, yeah.
And how from one to another, how do you solution how?
So this is all coming up with one, like one plan, right, or one policy, and then we're doing multiple rollouts of that. So with uncertainty in our state estimation, and then uncertainty in the dynamics, and that all comes from, that's all a learned model that's learning what that uncertainty will be. There's also uncertainty in the like system identification level. So when I get down to here, so the system ID transformer is also probabilistic. So initially there's a lot of uncertainty in our system identification, in our friction and mass and everything. And that propagates over to the dynamics that says, so that all of that kind of probability flows through. And then like when we do these kinds of rollouts, it's, if they're all trying to achieve the same control policy, just in different worlds, those will end up with different outcomes. Right? And then the idea with the divergence constraint is we really want to avoid the places where those outcomes diverge significantly.
I think through the MPC loop, it goes to the next trajectory as well, right?
Yeah, and then it's a receding horizon, right? So, we'll repeat it, shift things forward. Next time.
More questions? Ready?
Mhm.
Thank you. I really love the link observer.
Yeah.
Translates to non-thinking side and regulation, because I think that's an open problem still.
Yeah.
Like skin, artificial skin or something.
Yeah, I mean, there's a lot of people working on artificial skin, including at TUM, right? And it's getting better. There's a lot of surface area to cover. And anytime you add a skin, now you're really changing the way you're interacting with the world, right? And so they try and make it really thin, but at the end, fundamentally, you're putting something between you and the world. So that's a challenge. And then you got to figure out how to deal with all that data. And historically, these things have been not very robust, right? So if you smack your foot against the ground, a couple times a second, then it's going to cause problems, right? So what we've done, I didn't talk about it here, but we have done some stuff with this direct drive hand of doing contact localization. If you're touching something rigid, this works pretty well, where you can actually figure out with no tactile sensing, just proprioceptive sensing. If I touch here, I can figure out where I must be touching along the link. But that relies on the fact that the thing you're touching isn't also moving, right? And so if it's also moving, then it just goes out the window. So that's why in the vegetation stuff, we're not trying to localize the contact at all, right? We just want to come up with, the link momentum is really saying, I'm touching something. We're not going to try and translate that into where on the surface we're touching, or how many things I'm touching, or even if we knew those, we don't know when I push it more, like what's the stiffness or damping, like how is that contact going to slide? How is the force going to ramp up or down? So we don't know, we don't have a model of the thing we're touching. So even knowing where we're touching is maybe less useful. So we just wanted, are we touching something? And it's really sort of inherently, are we touching something that's stopping us from making progress? If we're touching something, but we're continuing to move, well, that's fine. right? But if we're touching something that's preventing us from moving our legs, that's when we have to react. And that's kind of inherently what we're getting from this kind of link momentum observer is when the thing we're touching is enough to disrupt our motion, then that's when we have to do something about it. And the key trick with the link momentum observer goes back to a name some of you might recognize down here, Sami Hadidin. And you don't have to do it at the acceleration level. You can do it at a velocity level. And so then it gets a little cleaner. You don't have to take a second derivative of your stuff. So
Cool.
Yeah.
I also have an add-on question. So you also a little bit teased like space robotics.
yeah,
Does the work also have like some applications on maybe sensor actuation failure? I think that is one of the main challenges of the robots out there. Like the wheels are not working anymore. And I feel
yeah.
like it
All
has
right.
some applications.
This is what I get for deleting all the extra slides at the end.
Perfect.
So I don't have a slide on it, but this work up here, that was using like a Mars rover kind of vehicle. Here we're showing trenching. So we're turning the wheel sideways and running it much faster to intentionally dig a trench in the ground. But all of this modeling work to do that trenching also works if your wheel happens to be stuck at a weird angle, or probably instead of running faster, if it's running slower than the other wheels. And so the newer work in that line from us is capturing the sort of mechanics, the terramechanics of the wheel-soil interaction at these kind of more extreme angles and speeds. And then we can use that to design open loop or closed loop controllers that compensate for actuator failure, either steering actuator or drive actuator that are either stuck or loose or whatever. Now once we kind of have a model for what the forces are in these extreme cases, then we can compensate for them with the other wheels. And it's a little hard to see. The other wheels are not driving straight, right? If you just had 3 wheels driving straight and 1 wheel doing this, you'll go in a circle.
Yeah.
It'll act like an anchor dragging. So you do have to compensate for that with the other wheels, right? And so in that video, it's just done by hand, but then more recently we can do that automatically.
Cool. We have one more last question. We're done.
Regarding continue what Willie has asked about for this like momentum observer. I think I have to read a bit to understand how it works. Like, is there an intuitive example, for example, for the puzzle for robot, and when it was trapped by a line or just a single line fine? Now the observer says, okay, now we are trapped, and intuitively how the lines move in this case. And can I understand it? Like,
Yeah. All right. So I
I
think the key here is when we're not touching something, we have a great model we have a good model of the legs, right? And it's only when we're touching something that we have a bad model. But that's all we need, right? We're just trying to figure out, are we touching something that's hindering our motion, right? And so we only need to model the leg when it's not in contact. So this avoids the need for a model of the thing we're contacting, right? So it's just rigid body dynamics for the leg. It does a moment. We're sort of comparing the momentum, so estimated momentum versus the predicted momentum, and integrating that up is kind of all it's doing. So that's using a model where we're not touching anything, right? It'd be much harder to have something where if I'm touching one thing and then I start touching another thing, now I don't have a model of kind of either version of the dynamics. But here we have our nominal dynamics. We assume we can model that reasonably well. And it's only when we're interacting with something that we don't know about that we will have an error that we can detect with this link momentum observer.
Great. Thank you very much, everybody. And thank you, Aaron, again.
Yeah, thanks for
And,
coming.